Hello, students. Have you ever watched a playground swing move back and forth? That smooth to and fro motion is what scientists call vibration or oscillatory motion. It's a repeated movement about a central position like the swing's resting spot. Now, imagine how many times the swing moves back and forth in 1 second. That counting number is what we call frequency, pronounced as frequency. It tells us how often something vibrates each second, and its unit is hertz, symbolized as Hz. For example, if a thing moves 20 times every second, we say its frequency is 20 hertz or 20 hertz. Isn't it fascinating that so many things around us vibrate constantly? Think of the buzzing of a bee, the strings of a guitar, or your own vocal cords when you talk. All have their own frequencies. Let's keep these exciting science terms in mind as we explore more about vibrations and sounds in this lecture. Can you think of something around you that vibrates right now? Pause for 15 seconds and observe. Ready? Let's dive in. Welcome back. Imagine you hear two different sounds, the roar of a lion and the chirping of a bird. How can you tell these sounds apart, even without seeing the animals? Two very important properties help us understand this amplitude and frequency. Amplitude measures how far the object vibrates from its resting position. A big wiggle or large amplitude means the sound is loud. Frequency is the number of vibrations each second. If frequency is high, like the chirping bird, the sound is high-pitched or shrill. If it's low, like the lion's roar, the sound is deep or low-pitched. So amplitude tells us about loudness, and frequency tells us about pitch. Think of amplitude as how strong the wave is, and frequency as how fast the wave vibrates. Now take a moment, pause for 15 seconds, and think about what might happen to the loudness and pitch of a guitar string when you pluck it gently versus hard. Got your idea? Great. We'll explore these concepts with examples soon. Now let's step into the world of invisible vibrations and waves. Look at figure 10.17 on your screen. Here, a thermocol ball which is extremely light is hanging right next to a glass tumbler. When we gently strike the rim of the tumbler with a tablespoon, the tumbler vibrates. These vibrations travel through the tumbler's surface. Because the thermocol ball touches the tumbler, these vibrations make the ball move too. It's like when a dance floor shakes and you feel the beat under your feet. This simple experiment vividly shows us how energy from one vibrating object is carried to another. This is called energy transfer through mechanical waves. It helps us understand the nature of sound and vibration. Now pause for 20 seconds and imagine how different the movement of the ball might be if you strike the tumbler very gently versus striking it very hard. What changes? Get ready. We will explore these changes in the next slides. Let's dig deeper into amplitude and how it affects the loudness of sound. Amplitude is simply how far something moves from its original resting spot while it vibrates. If we take our thermocol ball experiment, hitting the tumbler gently causes a small vibration, while hitting it harder causes a bigger vibration. Now here's where it gets interesting. Loudness is proportional to the square of the amplitude. Say you double the amplitude. The loudness doesn't just double, it actually becomes 4 times louder. This explains why banging a drum hard produces thunderous sound compared to a soft tap. Checking out table 10.1 on your screen, we find examples of sounds we hear every day, and their loudness in decibels, or dB. Breathing quietly is about 10 decibels. A normal conversation is 60 decibels, and factory noise can reach 80 decibels. Sounds above 80 decibels can even hurt our ears. Let me ask you, if you double the amplitude of a sound wave, what happens to the loudness? Pause for 20 seconds to ponder. Ready? Louder by a factor of 4. That's the power of amplitude squared. Welcome to the vibrant world of sound intensity. As we saw, loudness depends on how large the vibration amplitude is. A baby's gentle cry has a small amplitude and a feeble sound. A roaring lion has a large amplitude and a very loud, powerful sound. The decibel scale, shown in Table 10.1, helps us measure sound loudness on a scale from 0 up to 140 decibels. For instance, normal breathing is just 10 decibels, very quiet and almost imperceptible. But busy city traffic pumps out 70 decibels, which can be tiring if we listen for a long time. Noise above 80 decibels may start causing discomfort or even permanent hearing damage over time. Always protect your ears in loud environments like factories or concerts. Now, think about the last time you were in a noisy place. What was the loudest sound you recall? Pause and reflect for 15 seconds. Sounds shape our world, be mindful of their power. Let's shift our focus to another amazing property of sound: pitch. Pitch is what makes sound seem high or low to our ears. And what controls pitch? Frequency, pronounced frequency. Frequency is how many times something vibrates in 1 second. Look now at figure 10.18 on your screen. At the top, a boy hits a large drum. Notice how the sound waves are spread far apart. This means low frequency. Low frequency equals low pitch, so the drum produces a deep booming sound. At the bottom, the boy blows a whistle. The waves are close together here, a sign of high frequency. High frequency sounds are high-pitched or shrill. Now, the scientific formula for frequency is the number of vibrations divided by time. Imagine a bird's cheep. It has a very high frequency. A lion's roar has a much lower frequency. Now, take a moment and pause for 20 seconds. Think. If you double the frequency of a sound, what happens to its pitch? Yes, the pitch becomes higher. Isn't that wonderful? Sounds with higher frequencies are sharper, and those with low frequencies are deeper. Have you ever noticed how your voice sounds different from your teacher's? Or how children's voices are higher pitched than adults? The reason lies in the frequency of the vibrations produced by your vocal cords. Children's vocal cords vibrate faster, producing higher frequencies, which results in higher pitch sounds. Women generally have vocal cords that vibrate at a higher frequency than men, making their voices higher pitched on average. Meanwhile, adults and men tend to produce sound vibrations with lower frequencies, resulting in deeper voices. This is why each person's voice is unique and easily recognizable, an amazing feature of sound. Take a moment. Now pause for 15 seconds and think about how your voice changes when you speak softly and loudly. How do the frequency and amplitude play a role? Amazing how science explains our everyday experiences. Let's wrap up today's session by summarizing the key points. We started with the idea of vibration, a back and forth motion that repeats. Amplitude tells us how big this motion is and is tied to how loud a sound is. Loudness itself depends on the square of the amplitude, so even small increases in motion can make sounds much louder, measured in decibels. Frequency tells us how fast these vibrations happen. The faster the vibration, the higher the pitch we hear. Think of a violin's high-pitched note versus a bass guitar's deep, low sound. This is frequency at work. These amazing properties explain why sounds are distinct and lively around us. Sound truly paints the silent world with color and emotion. Take a moment to reflect on sounds before and after this lecture. What will you listen to differently now? That's the wonder of science continuing in your curiosity. Now it's your turn for a fun interactive question. Imagine you are playing your favorite musical instrument. If you play the string softly, the sound is gentle. If you play it hard, the sound is louder. Now think about this. If you double the amplitude of vibration on the string, by how much would the loudness increase? Pause for 20 seconds and think carefully. Did you say it would become 4 times louder? That's absolutely right, because loudness depends on the square of the amplitude. Doubling the amplitude means the loudness increases by a factor of 4. Imagine hearing your favorite song suddenly become 4 times louder. What a thrill! This scientific principle helps sound engineers and musicians control volume and tone beautifully. Here's another question for you, young explorers. Imagine you can change the frequency of a sound wave from 200 vibrations per second to 400 vibrations per second. What do you expect to happen to the pitch? Pause for 20 seconds and picture how a bird's tweet sounds compared to a lion's roar. What differences in frequency and pitch do you notice? Yes, you got it. Increasing the frequency raises the pitch, making the sound sharper or shriller. This is why a whistle's high-frequency vibrations create a piercing sound, while a drum's low-frequency vibrations make a deep, booming sound. Frequency is like the speed dial of sound's tone. Science is all around you. Let's see how the properties of sound show up in daily life. Musicians carefully tune their instruments by adjusting frequency, so each note sounds just right. When you turn the volume knob on your music player, you're changing the amplitude, making the sound louder or quieter. Hearing aids help those with hearing difficulties by amplifying, increasing amplitude, the sound waves, making everyday sounds clearer. In hospitals, doctors use ultrasound, very high-frequency sound waves, to see inside the body without pain or surgery. This amazing technology depends on our understanding of how frequency and amplitude work in vibrations. Next time you listen to music or visit a clinic, remember the science behind the sounds? Let's revisit our practical experiment with the thermocol ball shown in Figure 10.17. When you strike the tumbler gently, the vibrating tumbler moves the ball slightly. Strike it a little harder, and the ball swings further away. This movement of the ball represents the amplitude of vibration. The bigger the swing, the larger the amplitude. It's a fantastic visual clue showing how vibrations carry energy. This means the louder the sound you produce, the greater the vibration energy you pass along. It also teaches us about mechanical waves traveling through solids. Think of the thermocol ball as a tiny witness to the invisible energy flow. Next time you hear music or knocking sounds, remember the vibrating dance of energy happening right before your eyes. Let's take a moment to picture yourself as one tiny particle on the surface of a drum. When the drum is hit, you begin to move back and forth rapidly. That's your vibration. As you move, you bump the next particle, passing on energy like a line of dominoes falling. This is how vibrations move through matter to create sound waves that travel through air to our ears. Imagine the thrill of being part of that invisible chain reaction that brings music and voices to life. Science is not just about facts, but about experiencing the beauty of nature's dance. Keep this image alive as you explore the wonders around you every day. As we conclude our journey today, remember that the world of sound is full of vibrancy and wonder. The amplitude of vibrations gives us loudness, telling us how strong a sound feels. The frequency decides the pitch, painting sounds with high shrillness or deep richness. Every whisper, shout, birdsong, and drumbeat is shaped by these invisible waves moving through matter. With science, we not only understand these fascinating facts, but also marvel at their beauty in our daily lives. So next time you hear a melody or a comforting voice, think about the tiny vibrations traveling fast to meet your ears. Thank you for joining me on this delightful exploration. Keep your curiosity alive and keep listening to the symphony of science around you.